So you've written down the domain and range of this function. Hopefully you all got the same as moi, and that is, so for f of x equal to 2 to the power of x, the domain is all real numbers. There's no restriction there, is there? And the range will be all real numbers again, except 0. Is that right? No. Real positive, yeah. So real plus, it should have been. So if you didn't put the plus there, make sure you do. Actually, you know what? I don't even know that need the without 0, do I? Just real plus will be good enough. Or you could have written 0 to infinity, or you could have written y is a member of real y greater than 0. Anything like that's fine. One of the things that came from the progress test was that there is still quite a bit of confusion over the set notation, which one you should use. I've tried to give you lots of different examples because they any of them are acceptable. You've got to be careful to use one of those and not just make up your own notation. Okay, so that's what it is. What I want you to do now, I'll put the graph back on so you can see it, is without graphing, what would the inverse, not the inverse function necessarily, what would the inverse domain and range be like? 30 seconds to do that. Okay, that's all you're getting for it. Did you get that? See what I did there? I just flipped them over. That's what you should have done as well. So the inverse function, the domain or the inverse, the domain and range flips. That's all. The domain and range flips. Inverse function, we need to make sure that it's that f of x and f inverse of x is 1 to 1, etc. Those kinds of extra features for an inverse function. We would need to make sure that they exist first before we could say it's a function, but we can always work out the inverse simply by flipping the domain and range. Yes, yes, yes. Okay, so what does that mean pragmatically? I'm going to go back to Desmos now. Pragmatically, that means for the inverse, I flip a y coordinate and the y coordinate and the x coordinate for all the coordinates. The x and the y flip around. That's all that means. All the coordinates flip over. So there was a problem on the progress test where you had to graph the inverse, graph the inverse function. And, all you have to do is pick the points and then flip the x and y and put those points in and then draw it in. So this is similar for this. That's all we need to do. So we can get a sense of the graph. So if x was 4, then f of x is 2 to the power of 4, right, which is 16. So what I'm going to do is I'm going to just cut out the calculation stuff and say my x coordinate this is the inverse, my x coordinate is going to be f of minus 4, and the y coordinate is going to be minus 4. There we go. That's that point there. Okay, so y is minus 4 there. Sorry, I should have said that a bit better. 2 to the minus 4, that would have been, which is minus 1 on 16. 1 on 16. Okay, I'm going to keep on going. F of minus 3. That's the y coordinate from the function, is now the x coordinate of the inverse. And we've got minus 3 here. There's the next dot. We've got minus 2 and minus 2. Can you see what I'm doing? I'm just flipping the x and the y coordinates of the original function, the 2 to the x function. Okay, so these dots here, these points, are the inverse of the coordinates here. The x and the y's have been flipped. I'll keep going. F of minus 1 and minus 1. F of 0 and 0. Unsurprisingly, in the y coordinate, sorry, the y-intercept of f of x equals 2 to the power of x becomes the x-intercept of the inverse, because the 0, 1 becomes a 1, 0, right? F of 1 and 1, f of 2 and 2, f of 3. I can't just stop until I've got it mirrored out. F of 4 and 4, right? So this is what we've got as the inverse. These are the dots that make the inverse of the exponential function. Does it look familiar at all? Okay, I'm getting a couple of faint nods, so we'll come back to it in a second. I flip these. Looking at the pattern here, can you kind of see what's happened to the asymptote? What's the asymptote going to be? The asymptote of 2 to the x, is y equals 0. It's that blue dashed line there. Yeah, M, correcto. X equals 0 becomes the asymptote of its inverse. So this is the inverse function. It is a function. You can see now that we've got the dots here that just visually, you can see from the 2 to the x graph, it succeeds with the horizontal line test, right? If I draw a line anywhere along here, it's only going to hit the graph once. So it is invertible. This function, this is definitely a function as well. It passes the vertical line test. So that's fine. The inverse is also a function as well. So that's fine. It's an inverse function, and the shape of it is like this. It is the flip of this. As usual, we can put the line of symmetry here as y equal x. We can see that this has flipped over here. We can see the y-intercept is now an x-intercept. The horizontal asymptote has turned into a vertical asymptote. So all of these things make sense in terms of what we've seen before in inverses. So here's the big question. It's okay if you don't know it. Not who recognizes, what is that shape that I've drawn? If I join the dots, dot to dot, what function would I have there? Yeah, it's a logarithm. Okay, so that is the shape of a logarithm graph. A logarithm graph is exactly an inverse to an exponential function. And that kind of makes sense, doesn't it? Because we know from our work last year as well as this year that if we have y equals a base to the power of x, then we know that, let's just do the inverse kind of thing. So if I said the usual technique for working out the inverse, we know we swap the x and y over. So that would be x equals a to the power of y. And then we need to make it in terms of y. So we're going to use our logarithm rule, which is that y comes down here, the base becomes the base of the log, and the answer to the a to the y becomes the argument of log base, of x. So it becomes log base ax, or sometimes you put brackets in it to show it's a function, log base ax. So there you go. So that kind of makes sense in terms of our understanding of logarithms as well. When I flip the x and the y, the result is a logarithm. Okay, you signed in? Cool. So that makes sense, I hope. Questions? Okay, so if I go y equals log base 2 of x, you can see that the line goes through all those dots there. So that's what the function looks like. Okay. So what I wanted to show you is just a quick preview of what the transformations do. It is as usual, really. At this point, I'm hoping that the transformations are getting to be more you're a little bit more confident with them. If you're not, then just keep on working at it. Every time we hit a function with transformations, it's important for you to have a go at it. So this is what the 2 log base 2 x minus 5 plus 1 looks like, for example. So we can see that it's translated 5 units across, and that affects the vertical asymptote. The vertical asymptote is now x equals 5 instead of x equals 0. Okay, so that's the nature of what the translation does. Okay, I've got a plus 1, which means, well, how about I get rid of the plus 1 to start with? You can see that by default, therefore, the next unit along would be where the x-intercept is, as it is there. The 2 means it's been stretched out, but we know that doesn't affect the x-intercept. So the x-intercept will be pinned there. But if I put a plus 1, then that value of 6 is now 1 more unit up. Oh, sorry, I couldn't get to fix there. Oh, it's not going to fix. I'll just put my finger there. So it's 6, 1, right? So what was 6, 0, because I've translated the graph up by 1, is now 6, 1. Okay? So it's the usual effects. That's how we go about plotting it. Okay, we work out how much it's translated, how much it's gone up, and then go from there. Okay, I'm going to go through an example of, here is a graph, here's how we go to sketching it. But does anyone have any questions about that? Okay, so really quick. Because you've done logarithms last year, I propose I just do a really brief summary of what it is now, and then I'll get into the example as fast as I can. So this can go into your summary book. I'm just going to say log base A of x because the shape of it's pretty much the same. I think from memory you can be given a base 2, a base 10, or a base E, and we'll look at base E tomorrow. Okay, so they're the bases that you can get according to the curriculum document. Of course, they could be any positive base. You can't have a base 0, you can't have a base negative. So but in general, log base AX looks like this. Oh, hang on, I'll do it nice and straight. Sorry? Mm. There we go. So that's the base graph or the parent graph. And transformations will then shift. You'll always get the same shape. It'll just shift whether it's stretched out or squished, which you can't normally see in a sketch anyway, but it'll shift vertically, it'll shift horizontally. That's the kind of thing you're looking for there. Okay, so I'll give you a chance to write that down. So really quickly, going to Desmos, you got the usual sorts of things. If I go x plus 5, then I will have the asymptote at a minus 5. So effectively, we're kind of solving for the... by the way, when I say argument, people in my class from last year will know what I mean. The argument is basically what I'm putting into the logarithm function. So the argument here is x plus 5. So if the argument is x plus 5, then the asymptote will be minus 5. The shape doesn't change. If I put a 5 here, it stretches out a lot more thinly, I suppose. If I put a 0.5 here, it'll flatten out, like so. If I put a 2 in front of the x just like that. Why did it do a translation when I put a 2 there? I just did a dilation of 2 here. Why did it also affect the asymptote placement? You should know. Tian. Yeah. So exactly as you said. The asymptote argument is 2x plus 5 equals 0. Solve for that and you get 2.5, like you said. However, again, just going further to what Tian said, if I take the 2 outside the bracket, which is why we encourage you to do this, if we take 2 outside the bracket, then I would have to change the 5 to 2.5. Okay, so if I expanded that, that would be 2x plus 5, like I had a second ago. So taking the argument out gives you the translation explicitly, as opposed to you have to figure it out. So taking out the dilation in this manner is always a useful thing to do. So now if I go to minus 2.5, it's now situated exactly where it needs to be. So there's the dilation, and we've seen the translation as well. We can go minus 1, we can go plus 10, we can do whatever. Okay, so keep that in mind. So without going into too much detail there, I hope you can see that if I have a translation to the right, then I'm not going to have a y-intercept. So whenever I translate past the y-axis, of course, there'll be no y-intercept to find, but the x-intercept will need to be worked out. If I go the other way, then there may be an x-intercept and a y-intercept that you need to figure out. So as usual, you should be thinking about the shape of your graph, maybe sketching it out at least quickly to get a sense of whether there's going to be an x and a y-intercept, and then actually calculate them so that you can sketch the graph properly. Remembering that intercepts are critical points, asymptotes are critical information on the graph. Okay, so that's the nature of the transformations. Does anyone have any questions about, sorry, I'll stay on Desmos, anything at all? Because if you don't ask, I will push on. Questions equals clarity. Q-U-L-A-R-I-T-Y. Questions equals clarity. Okay, we shall be quick and move on then. That's C-W-I-C-K. So let's go through an example. So this can go into your summary book. I'm not insisting, I'm just suggesting. I've picked a fairly straightforward one just so that I can get it going pretty quick, and then you can go from there. You can ask lots of questions as you go into the harder ones in the textbook. So y is equal to 2 log base 2 of x minus 5 plus 1. So with practice, well, first of all, you should be able to list the not in order, but you should be able to see which what the transformations are, right? Dilation of 2 in the direction of the y-axis, a translation of 5 units to the right, 1 unit up. So straight away, we're going, oh, thank goodness, the translation to the right. Why thank goodness? Yeah, one less thing I have to work out. If you try to find the y-intercept, it'll come up with a does not exist kind of error. So it's fine if you don't see that, as long as you go, when you get to the does not exist point, you go, oh, that's right, because it's gone to the right. Plus 1 is a translation up of 1 unit. Does that mean that we don't have an x-intercept? No, it does not mean that at all. It means the x-intercept is probably going to be nasty. Okay, so let's put it all together. Shape. I know it's still going to be that shape. There's no reflections, so it's going to be this sort of shape. Asymptote. I've translated 5 units to the right, so it's going to be x equal to 5. That's going to be the equation of the line, not a function, but it is the equation of the line. Do write x equals 5. The asymptote is not 5. Do not write 5 down. You will lose half a mark for writing 5 down. That is not the asymptote. The asymptote is an equation. Okay, if you wanted to, you could write y-intercept d and e if you want to be consistent with the way you work things out. I'm not going to write that down because I just tend to write the things I need rather than everything. X-intercept is at y equals 0. So let's work it out. 0 is equal to 2 log base 2 of x minus 5 plus 1. So minus 1 is equal to 2 log base 2 of x minus 5. This is where you're hoping it's in the calculator section, so you can just use the solve function in your calculator, because it's like, oh my gosh, do I really have to do this? And of course the answer is, yeah, you do. You can't use your log rules until you've got the log all by itself, just a reminder. So I have to divide both sides by 2, and I will get minus a half is equal to log base 2 x minus 5. Now I can use my log laws. Now I can use in this case, I'm going to use the log definition. And the log definition is a to the power of b equals c. So I can put x minus 5 here is equal to 2 to the power of minus a half. So x is equal to 2 to the minus a half plus 5. There we go. That's your silver standard answer. Should we go for gold? Let's go for gold. Which equals 1 on 2 to the half plus 5. Which equals 1 on root 2 plus 5. That's your gold standard answer. You've turned it into a root. Should we go for platinum standard? Just for giggles? Who said no? Was it you, Hamish? Get out! How dare you? I'm really glad I've captured it on video. It wasn't you, Hamish, and I've captured it on video both. I'm pretty sure. I'm confident it was Gabe. No? Okay. All right, thank you. So the platinum standard would be that. And anyone who's cross-eyed at that point can't remember how to rationalise denominators. I multiplied top and bottom by root 2. Root 2 times root 2 on the bottom is 2, and 1 times root 2 on top is root 2. Typically, you rationalise denominators because technically common roots like root 2 you might know, like root 2 I think is 1.4. So by having root 2 on 2, you can say, oh, okay, so that's about half of 1.4, so it's about 0.7. So you can say that's going to be 5 and 5.7 roughly. You know, so it gives you the capacity to just figure out roughly where to put it on the number line. That's why you rationalise roots, so you can do that kind of thing. So now I have to graph it. I have to do that on the next page, which is a bit of a bummer because then I can't see all my working out. So what have I got? I've got an asymptote at x equals 5. So let's get that going first of all. So let's go for a nice set of axes. Which I should have had a bit more room on the right and not so much room on the left there. So that's a rookie error. I'm going to put my asymptote in here. So that's x equal to 5. And then I'm going to put my graph in. Probably a bit too steep. There's a bit of muttering going on. Is that because you're bored or is it because you've got a question? Or it could be just rudeness, but I'm sure that's not the case. No? Okay. I'll draw my own conclusions. Yep. Yep, okay. So here is where you could write 5.7 if you've worked it out. Or you can write, sorry, I had it the other way around the answer, didn't I? What is it? Root 2 on 2 plus 5. So you can write that in and you're pretty much done. If you wanted to, you could also put one other point in, And that's just using your translation knowledge, right? So using my translation knowledge, I've gone up 1 unit. So just make sure you're paying attention to this because translations were a bit weak in the progress test. If you have a look at this, I know that by default, this point here is 1 unit away from the asymptote, but this says it's gone up by 1. So 1 unit away from the asymptote would be 5, so it would be 6. It's gone 1 unit up. So that would be, that point there would be 6, 1. And that's a really nice, easy point. And putting that point in gives us that real sense of scale there that otherwise would be missed. So if you've got time, I'd put that second point in because it does really help give that graph a sense of scale. Okay, so questions. Right, we have 25 minutes left in this lesson, roughly. What I want you to do is I want you to go to here, your learning schedule, but I'll keep it up on the screen anyway so you can just look at it from here. For this week, it's a test at the end of next week, by the way. So we are at the logarithm graphing. You can see here that I've got exercise 5E, question 3 here, and exercise 5F here. Give me a moment and I'll make these links to the interactive textbook. I just hadn't quite got around to doing that. I'll put an appointments list up on the board. You come up and ask me questions when you're getting stuck on stuff. Otherwise, just maximize your practice time, dudes.